So let's look at what all are the components of this particular cluster. So I talked to you about special networks. I said that we do have networks which are very special, which are not your traditional 10 gig networks, but you have InfiniBand networks which gives 100 Gbps or 200 Gbps also. So that's one of the part of your overall cluster component, so that you can communicate faster, not just compute, but communicate faster across nodes also. Obviously, the users need to access it from outside, so you need to have a network which is connecting it. You have your nodes where you're going to run all of your jobs, which means you have the cluster nodes or the compute nodes where the actual computation will happen. Like in an environment, you will have a CPU, GPU nodes, and you will have X number of them, and all these nodes are connected to each other via this high-speed InfiniBand network, so that you can spread your work across those nodes and they can communicate faster and you can accumulate the results also. You also need that every node does not have its own storage, but you have storage which is like a network file storage, which means all the nodes see the same storage. So if you access one node or versus the other node or the third node, it doesn't matter. Your home directory or your all of your files are actually mounted, and they are there in this particular storage, which is common for all the nodes. And as you can see here, especially in AI also, you require a very high speed storage, because if you talk about AI, you're not talking about even nowadays gigabytes of images or gigabytes of data. We are talking about terabytes of data that needs to be trained or analyzed on. So you need also a very high speed storage, so that you can basically access, not just compute faster, not just communicate faster, but also read the data or the storage very, very fast. And finally, the login node, which might not be something new to you, but all the users, they basically don't access the node directly. They are given access to something called as a login node. In this login node is where you ask for resources, and based on the available resources, you get access to one of the nodes. So you are not directly going to go and access the compute nodes. So every user comes to the login node, asks for the resources, then they are given that compute nodes, and then they execute their work, and then they are done. And this is what generally the component of any cluster. Even in the cloud environment, you will see almost the same setup, just that there will be some additional software component to maintain it, which we'll talk about. So I talked about all of the components of this cluster environment. Now let's move on to the second part. I said that I'm going to ask for resources and I need to ask it. Now, what is that software that I require to do this? In order for you to get a feeling of how the cluster looks like, in the end, if we get time, I'll also show you this. I put one of the NSM cluster link here, which kind of shows how the National Supercomputing Mission cluster configuration or the cluster environment looks like, how many compute nodes are there, how many login nodes are there, how much is the storage, how are they connected to each other via the InfiniBand network. So you can go and look at this specification and see how these clusters traditionally look like, in case you don't have access to one cluster at this point of time. So I told you that you need to access this hardware, right? And you need to ask for it. It's not by default given to you. And that is done by a software or a framework which is called a scheduler. And as the name says, the job is kind of very clear, right? So the idea is simple, that you have X number of compute resources which are known to the scheduler, or it's part of the configuration, which means that I know that how many nodes I have. These nodes have how many CPU cores, how much memory, how many GPUs. All of those parts are known to the scheduler, which is the manager. The user who comes to this cluster submits a work or a job. As you can see, there will be multiple users. Every user submits a job. What is this job containing? I will come to that part. And then the Slurm is the one, the manager basically sees what do you require, and based on what is free and what provision has been provided to you. Like if you can only ask for one node, then you will get only one node. And the slum basically takes your job and allocates a node for you so that you can go ahead and start executing on that particular node. Now here you can ask for 5 nodes, 8 nodes based on what is the compute requirement from your side. So you see that there is in between scheduler as a manager which comes into the picture, making sure that all the policies are also met. Like everybody gets a fair share and there is no coordination which is required because everything is being done via the slum. One of the most popular scheduler is called as Slurm, which is simple Linux utility for resource management. It started with a simple resource manager. It has almost like 5 lakh lines of C code. It is very easy to use. You can run it on your PC if you want to, by the way. If you would like to do that, you can do it. Generally, it's used in a cluster environment. But if you'd like to test out on your own laptop, you can run both the manager and the compute node. You can make your laptop as both of it and try out if you would like to, just to get a feeling. But we recommend you to leave this job of management and installation of Slurm and everything for the cluster admins. And if you are a cluster admin, yes, please do go ahead and do that. It's the glue for a parallel computer, as I said, to execute parallel jobs. And that's what is the role of the scheduler. If I look at it from an architecture point of view, the Slurm basically consists of two main components. The first one is called as a controller. The second one is your compute nodes. So as you can see here, this is your login node. I told you there are two types of nodes when I showed you the cluster. The login node and the compute nodes. The login node is the one where you have the controller. It is run as a daemon. The daemon name is Slurm CTLD. So you can see here it runs as a daemon, and basically a user is going to ask this daemon which is running to basically allocate certain compute resources. The compute nodes is going to run another daemon which is called as slurmd. This slurmd is basically the daemon which is going to listen to the manager, and basically the slurmd will tell the manager that I am free, or how many resources are free and all those things. And based on what you've asked for, the slurm can basically, based on the policy defined, assign that particular node for the job that you have in mind. There are some optional component also which I am not covering in this particular session, but I hope you get the idea. So it's like a client server, right? Or a manager and a slave, like a model where you are going to have a master and the master is going to give the jobs to the slaves who are going to basically do it and then give the results back to the master and they basically work on it. So I have provided the link for more information if anybody would like to see how this Slurm functions into more detail of this Slurm architecture. So what can you ask for to this manager, right? So you can ask different things. You can ask a node, which means how many compute nodes do you need? You need one computer, two computers, three computers, four computers. How much memory do you require per node? Like, do you need 1 GB, 2 GB, 4 GB, 8 GB? You can ask for the number of parallel tasks that you're going to run. Like, if you're going to say, you know that you have a task which can utilizes only 4 cores, so you can say I need within a node, I need one node, and within a node I need only 4 cores. So if your cluster, if your node had 16 cores, it will take away those 4 cores and give it to you, while the rest all will be free for somebody else to use. You can also ask the number of GPUs you want that in that particular node. You can also define some quality of service, which we'll skip for this session. It's more towards the admin side. And also you can define other parameters, number of tasks that you need per node, and do you want exclusive access to it, or you can share those resources with somebody else. And there are different things that you can ask. I'm going to show you a live demo of this so that you get an idea of how this overall thing works. There are certain commands which are required for you to ask and find more details about this overall thing. Like there is a command called as sinfo. Sinfo will tell you all the resources which are there on your cluster, so that you can get a feeling of how many resources are there, how many of them are free, how many of them are abused, and who is using it, and all those things. Similarly, you can check the jobs that you have submitted. Are they done or are they not done via commands like sq? And I'm going to show you a view of the same. Can one of the admins basically confirm if you are able to see the terminal?
Yes, Bharat, it's visible.
Okay, thank you. So I hope you are able to see the screen, and I am basically logged into a cluster. This is our internal cluster. One of the requirements for you, even though we are showing a demo, is that in case you would like to do a hands-on on the system, you should have access to one of these clusters. And there are various clusters which are part of NSM and all. Or if your college has one of the cluster, you can do the same demo there as well. So the first thing I'm going to check is running a command called as sinfo. You can see here this sinfo has given me details about my number of nodes. So you can see here it says that I have nodes. The node name is DGX0180 to 0189, and there are 10 nodes. And all of these 10 nodes are idle at this point of time, which means there is literally no work going on this machine. How can I check it? I can again do SQ, and you can see here that I see that there is literally no job which is running at this point of time in the cluster. So I can also do, so it is, I'm privileged not to see all of these things, but you can get more information about it, like what is the time limit, and they were up from how much time, do I have the root privilege and all. But uh, let me give you an example of how I can actually run a particular job and ask for the details of this particular node. So what I'm going to do is that the slides will be available to you in case you want to do that, but I'm going to show you a demo of how I can ask for a node and run some task, right? So you can see here I'm saying srun. Srun is a way for me to access and ask for a node. How many nodes I'm asking? I'm asking that I need only one node at this particular point of time, and I need only 5 cores, or I'm going to run only 5 parallel tasks in it, so I need only 5. And then I'm also saying other things, so you can skip this particular part. But then I'm also saying that I believe my work will get over in 4 hours, so I need it only for 4 hours. I'm also mentioning it that I need one GPU because I'm going to run a accelerated computing job, and I need a GPU to make sure my network kind of trains much more faster. So I'm asking it for one node having 5 cores, and then also the time for which I need it, and also the number of GPUs I need it. And I'm saying that I need basically a terminal which can be opened. So once I enter this, basically you can see here that I moved from my login node. One thing which I forgot to tell you is that you can see here this is the login node, and when I ran this command I have moved away from the login node to this node, which is DGX0180, which was my compute node. So let me exit once more and show you that, see, my login node might not even have a GPU. So if I do NVIDIA SMI, which is the command to find out if I have any GPUs or not, you can see here there is no GPU which is available, and I should not run anything on the login node. So I'm going to ask it for resources, and then if I do NVIDIA SMI, I can basically see that now on that node I have asked for one GPU, and I am basically getting one NVIDIA Tesla V100 card, which is given to me at this time, right? And if I do a SQ also, you would see that it is telling me that I am basically running one particular job, and that job has been allocated on DGX0180, right? So it will give me all of those details. And now you can see earlier all of my machines were empty, but if you see now sinfo, you can clearly see that now only 9 machines are empty, and one of these machine is actually in mixed state, which means some of the part of this machine is used while some of this part is still available. for me to be given to some other resources. So this is how you can see. In fact, let me just give you another example and ask for 2 GPUs instead of 1 GPU. And if I'm lucky, I might get that in case the resources are available. And I saw that there are resources which are available. Now you can see here that again I am in the same node, which is DGX0180. Earlier, when I did NVIDIA SMI, I saw only 1 GPU, but now I ask the resources to give me 2 GPUs, and suddenly I start seeing 2 GPUs. Now I can run a job which can run across 2 GPUs or in parallel. And this is how the overall basically cluster ease works, right? So this is how multiple users can actually access and ask for more and more resources. Today I have 10 nodes, tomorrow I can add 2 more nodes, and then it will just add it to my existing list. And I can also cancel the job. Like you can see here, there is SQ. I can do S cancel and give the ID which is assigned to that particular job, and it will basically cancel that job. And you can see as I cancel this job, I came out of the compute node and I am back on my CPU node, and there is no job which is running, and all of the machines are again free for somebody else to use. Now you can see here that how easy it was for me to basically just use these resources and keep on increasing these resources, and I can submit a job as much as I need it for be accessible, right? And let me also show you another example of how I could on this cluster also run a container job. So I'm going to run a container job. I already have a script. You already had a session on how to run containers. So I'm not going to run a container. I'm not going to show you that command, but the script will be provided to you in case you want it to run. But I'm running a container job, and that container job is going to basically give me certain resources. Oh, I'm sorry. This is my mistake. I need to first allocate a resource for myself. So the first thing I'm doing is I'm getting a GPU node. You can see here that I am getting a GPU node, which is DGX0180. Now I'm going to submit the job of running the container for making sure that I get access to the node. I have got access to the node. You can see here I am in DGX machine, which is having the GPU, and I'm running a container. And let me just do one more step. This step is something which is required for port forwarding. For now, you don't need to worry about this step, and you can forget about what it means. And so I just ran a particular container, and in this particular container I'm going to basically run a TensorFlow job. So let me open my Jupyter notebook. It was showed as a demo to you. Hopefully I've got the resources and I am able to, like, not yet. Yes. So you can see here that after I launch the job in the container, I am running this Jupyter inside the container notebook, and I can now start doing anything in this particular Jupyter notebook, which is going to run on the machine. Like this particular container is a TensorFlow container, and I can just run the TensorFlow here. You can see here that I'm importing TensorFlow as TF. I'm using Keras, and then I'm asking for the TensorFlow version, which is 2.3.1, and I'm asking if I have a GPU with me or not inside this container. And you can see here it says that I have a GPU allocated to this particular container, and you can see here that I'm able to do this. So again, just to repeat, I showed you a demo where I went to the GPU, and after that I ran the container on that GPU node, and it was I ran within the container the Jupyter notebook, and I could run this Jupyter notebook and run TensorFlow inside it. Now, some of you were asking in the last lecture on how does it matter whether I need to do any installation or not. Let me just show you one part. On this machine, sorry about this. On this machine, there is no TensorFlow installed. There is practically no TensorFlow which is there on this machine. I have not done any kind of installation. In fact, it says that module TensorFlow has no attribute called as version. So it is not having any installation of TensorFlow on this machine. In order for me, without to do any installation, I just imported a container and I started running it in form of a container, and I started accessing it on my Jupyter notebook. So this is the advantage, so that you can keep your cluster clean. I basically don't have to install TensorFlow, Keras, or any other software. I can just have containers on my machine and I can just give it to the cluster to run and keep on accessing it. And tomorrow, if I want to transfer it from this cluster to the cloud, which is the example which I showed of cloud bursting, I can take this container and deploy on the cloud of Amazon and all, and just start running it there without having to do any kind of installation. And that's the advantage that you get with the container environment. So this was a quick demo in terms of what a cluster is, what is the advantage of using a cluster, how can you ask for resources, how you can see how many resources are free, how you can cancel. Once you have got the resources, you can run a container, which you have saw in the previous lecture, and then open Jupyter notebooks or whatever you want to do, have a very clean installation, not having messed up my system, which is a cluster, via the containers, and can deploy it anywhere on the cluster, on my machine, on the cloud, and keep it as clean as possible. Now, this is very important, especially if I talk about enterprise computing, or if you're trying to run all of these jobs where you need quality of service. So far, what you have seen was the part that we have looked at was the need for accelerated computing, the need for software stacks like virtualization, the need for containers. Then we talked about the need for not just one system, but multiple systems connected to each other in form of a cluster and making things happen. But what I'm going to talk about now is kind of a teaser for the upcoming lectures, which will be delivered in the next set of in this particular series, right? So when I showed you an example, what I did was I took the resources via the scheduler, and then I started looking. I just started running it and ran the Jupyter notebook, right? So what it did was it did some amount of reservation for your CPU and memory, right? But as I said previously also, that the containers had certain restraints, so you need more limit controls. You need better scheduling. You need better policies of scheduling, which is there. Like Slurm already provides the scheduling policies like fair share and all those other kinds of scheduling. What you might also require is some kind of a load balancing, right? Because you might not have an instance where you are putting a lot of load on only one node or one part of your cluster while the other cluster is almost free. So you need to distribute the load among the container instances also. You need to do certain amount of health checking, like if there is any problem or if there is a faulty container that needs to be destroyed or replaced. So certain amount of health checking. What is the fault tolerance, right? If the you can create container automatically if a particular node fails. If you see, even if one particular node of Google or when you do search fails, doesn't mean that your the whole network is down, right? You will still be able to do that. What it does is it shifts that particular instance to another node, and that happens behind the scenes for you without you having to worry about this fault tolerance part. But this is something which happens behind the scene. Also, you can scale it automatically, right? Like a container can be added or removed automatically. So you can do auto scaling. So if I talk about a particular environment in AI, I'm not just talking about Scheduling is one small part of the real world environment where all of these things happen. You need to do load balancing, you need to do health check, you need to do fault tolerance, you need to do auto scaling, you need to do resource limit control. Now, all of this is happens via this tool called as orchestration. So what you're trying to do is not just schedule, but you're trying to orchestrate to make it really having a quality of service and having a lot of automation and on-demand access like you get in the cloud, right? That's what you see in the cloud without you having to know about all of this. Everything behind the scenes is running. When you do any search, there are machine learning and deep learning algorithms running on the Google when you do any search or anything like that, right? Or if whatever translation, like if I say something, it translates from one language to the other. All that is happening behind the scene in this particular cluster environment for you. What we are trying to do in this series is to expose you on what those things are. Now, that overall thing is called as orchestration, which means you're trying to orchestrate all of those features and making sure you're following all of those principles and optimally utilizing the resources. One of the orchestration layer, the most famous one out there, is called as Kubernetes. Kubernetes, you can think of it as an operating system for your cluster. Currently, you have heard this term operating system where you have a single machine and you're trying to access it. Now, for a cluster, you can think of Kubernetes, which is doing many of the things that operating system does, but for all the resources which are across the nodes and not just on one particular machine. You can think of it as a higher level operating system which takes into consideration all of the resources of your cluster. These clusters can be on premise. We looked at one example, which is in your premise. It can be a laptop also as one of the component of that cluster. It can be in the cloud or it can be hybrid. We looked at the cloud bursting part, right? So Kubernetes as an orchestration would look that if it is happening on premise, if you have resources, it can keep it here. But if you are exceeding the resources, it can do a burst to the cloud and run the same thing on the cloud also without you having to worry about it. So it can take this particular complex scenarios that we talked about some time back. It can be helped to manage all of these clusters, administer user access, launch containers, and expose all of this as services. Now that's the part which is used and very heavily deployed in any of the installations that you see of artificial intelligence. So it's more than a cluster. It's not just about scheduling, and it is much more than job scheduling. It's about orchestration. Traditionally, the cluster has been very uh, heavily tied down to high performance computing applications like molecular dynamics, computational fluid dynamics, and all, while orchestration is still very much relevant to the artificial intelligence space, and it is especially adopted by the enterprise segment with a large across all of them. It provides you and helps you in deploying very complex AI pipelines starting from training to inferencing. It provides you meta schedulers where you can define your own scale. Like Slurm can be one of the scheduler which is plugged to Kubernetes to do fair scheduling. You can scale up and scale down. And all those features are part of orchestration, while a simple job scheduler can do only few things, like it gives you bare metal performance, but it does not have this capability of scale up or scale down. It is tied down and it is very highly tuned for leveraging the best performance, which is primarily used by the researchers working in the high performance computing domain. So in the next set of lectures, what you're going to see is how to use Kubernetes and how this AI behind the scene works, and whatever you do, what happens on there. With that, I am done with the lecture which I had